And now in this lecture we'll find out the area of the green shape. In the drawing we have a circle. We know that the radius of this circle is equals to 2 units, r equals to 2. In addition, we know that inside this circle we have here peripheral angle ACB. Peripheral angle ACB equals to 70 degrees in its size. And we also have the common external point P. From the common external point P, we have two tangents to this circle. Tangent PA, that is tangent to this circle at point A, and tangent PB, that is tangent to this circle at point B. And our mission is to find out the area of this green shape. So first of all, we join points O and B together by straight line. Point O is of course the center of the circle. So point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of this circle R, that is equals to 2 units in its length. So we can implement in this drawing rule 2 or rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle that we also have tangent AB, that is tangent to this circle here at point M. And we also have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing we have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn, to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. Likewise, according to the sum rule, here we have the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. In the next step, I present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have the peripheral angle ACB. This peripheral angle ACB is subtended on this arc AB. And peripheral angle ACB equals to theta in its size, theta degrees in its size. And we also have in this side this circle the central angle AOB. This is the central angle AOB that is subtended on the same arc AB. And therefore, according to this rule 13, the central angle AOB will be twice as large as the peripheral angle that is subtended on the same arc. And because of the fact that the peripheral angle ACB is equals to theta, therefore the center angle AOB that is subtended on the same arc RKB will be equal to 2 theta. We can actually implement rule 13 in our drawing. Why? Because in our drawing we have this is peripheral angle ACB, this peripheral angle ACB is equals to 70 degrees in its size and is subtended on this arc RKB. In addition, we have also the center angle AOB. The center angle AOB is subtended on the same arc RKB. And according to rule 13, the center angle AOB will be twice as large as the peripheral angle ACB that is subtended on the same arc RKB. And because of the fact that the peripheral angle ACB equals to 70 degrees, it means that the center angle AOB that is subtended on the same arc will be equal to 140 degrees. Okay, it is twice as large as the peripheral angle that is subtended on the same arc RKB. So peripheral angle, the center angle AOB is equals to 140 degrees according to rule 13. In the next step, we will join points O and P together by a straight line. By joining points P and O, we created here two right angles, the right angle AOP and the right angle AOB. In the next step, we prove that those two right angles can go into each other. So I write it down, we prove that the right upper triangle AOP, this right angle AOP, is congruent to the right lower triangle, triangle POB. So, why those two right triangles can congruent to each other? First of all, side AO of the right triangle AOP is equal to side BO of the right triangle BOP. Well, because both two sides are the radii of this circle, therefore they are equal to each other. The radius of this circle equals to 2. So, side AO equals to side OB, or side AO equals to side BO. Both the radii of the circle is equal to 2. In addition, side OP is a common side that belongs to both triangles, so I can write down that OP equals to itself as a common side that belongs to both triangles. So side OP equals to itself as a common side and finally, side AP in the right triangle AOP is equal to side PB, so side BP in the right triangle BOP. AP equals to BP according to rule 2. I will remind you quickly what is rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle and we also have this common extreme point, point P. From the common extreme point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. This is to say PA equals to PB. We can actually implement rule 2 in our drawing. Why? Because in our drawing, we have the common extreme point, point P. From the common extreme point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. Or AP equals to BP according to rule 2. So I can prove that all the three sides of this right triangle AOP are correspondingly equal to all the three sides of this right triangle BOP. Therefore, those two right triangles can point to each other according to side rule. So I write it down. The right triangle AOP is congruent. This is the sign of congruent to the right triangle BOP according to side rule. And from the fact that those two right triangles can point to each other, we derive that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can point to each other, therefore the two corresponding angles, those two corresponding angles must be also equal to each other. So this is angle AOP. And it is equals to this angle, this is actually angle BOP. So if we define one of those two equal angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. So if this angle is alpha, then the other angle also equals to alpha. And alpha plus alpha is equals to this angle, that is 140 degrees. Again, alpha plus alpha equals to 140 degrees. So I write it down. Alpha plus alpha equals to 140 degrees. So 2 alpha equals to 140 degrees. Here we divide this equation by 2. And finally we get that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. Okay, this is angle alpha is equals to 70 degrees in its side, and this is also angle alpha is equal to 70 degrees in its side. In the next step, we'll find out the size of side AP. What is the size of the length of side AP? So we'll focus on the right triangle AOP. In the right triangle AOP, tangents 70 degrees. What is the value of tangent 70 degrees? In the right triangle AOP, tangent 70 degrees is equals to AP over AO. AP over AO. Repeat again. In the right triangle AOP, tangent 70 degrees equals to AP over AO. So AP is the missing side, so we leave it as it is. So it is AP over AO. AO is the radius of this circle that is equal to 2. So we substitute AO by 2. We substitute AO by 2. So if we found out that tangent 70 degrees equals to AP over 2. Tangent 70 degrees is 2.75. This equals to AP over 2. AP over 2. Here we'll multiply this equation by 2. And finally we'll get that AP equals to 2 times 2.75. 2 times 2.75 is 5.5. So for we found out that the length of side AP is 5.5. The length of this side AP equals to 5.5 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of the green shape equals to the area of the right triangle AOP plus the area of the right triangle BOP so the area of the right triangle AOP plus the area of this right triangle BOP will give us the area of this quadrilateral AOBP. Okay, the sum of the areas of those two right triangles will give us the area of this quadrilateral AOBP. And we have to subtract from the area of this quadrilateral AOBP the area of this sector AOB. So it is minus the area of sector AOB. Repeat again. From the drawing it is very easy to see that the area of the green shape in total equals to the area of the right triangle AOP plus the area of triangle BOP. That will give us the area of quadrilateral AOBP, and then we have to subtract from the area of quadrilateral AOBP the area of sector AOB. This will give us exactly the area of the green shape. So first of all, so this is sector AOB. I will explain you what is a sector. A sector is part of a circle. The green shape AOB is a sector that is part of this circle. The green sector AOB consists of two legs, the leg AO and the leg BO. Both those two legs are the radii of this circle that is equal to R, therefore they are equal to each other, of course. And so the green sector AOB consists of those two legs AO and BO, and the arc AB that is located between those two radii AO and BO, or the arc AB that is located between those two legs AO and BO. And the angle between those two legs AO and BO is this angle theta. Okay? So what is the area of this sector AOB? The area of this sector AOB will be equal to the area of this circle that contains the sector, that is actually pi r square, times the angle between the legs of this sector, that is theta, over 360 degrees. Repeat again, the area of this sector AOB equals to the area of the circle that contains the sector that is pi r square times theta, that is the angle between the legs of the sector, over 360 degrees. So AOB, here, the round line above AOB is the sign for a sector. It means sector AOB, and the squared brackets is the sign for the area. So in total, this expression means the area of sector AOB is equals to pi r squared, that is the area of this circle, times theta, that is the angle between the legs of this sector, over 360 degrees. So if we found out that the area of the sector AOB equals to pi r squared times theta over 360 degrees. Okay. And we have already found out that the area of this green shape equals to the sum of the areas of those two right triangles. That will give us the area of this quadrilateral AOBP, and then we have to subtract from the area of this quadrilateral AOBP the area of this sector AOB. This will give us exactly the area of this green shape, Again, the area of the green shape in total equals to the sum of the areas of those two of the right triangle AOP plus the area of the right triangle BOP, that will give us the area of quadrilateral AOBP, and then we have to subtract from the area of quadrilateral AOBP the area of sector AOB. Okay, we have to subtract from this quadrilateral AOBP the area of this sector AOB, and this will give us the area of this green shape. And because of the fact that we have already proved that this right triangle AOP is congruent to this right triangle BOP, so they congruent to each other, therefore they have also the same areas. Okay? And because of the fact that the area of triangle AOP is equals to the area of triangle BOP, we can substitute the area of triangle BOP by the area of triangle AOP. We'll do it now, and we'll get that the area of the green shape in total will be equal to the area of the right triangle AOP plus the area of triangle BOP, that's equal to the area of triangle AOP. So we substitute the area of triangle BOP by the area of triangle AOP. So it is plus the area of triangle AOP again. Minus the area of sector AOB. The area of triangle AOP plus the area of triangle AOP is 2 times the area of triangle AOP. Minus the area of sector AOB. So what is the area of triangle AOP? What is the area of this triangle AOP? Actually, the area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base of this right triangle AOP is AO, so the base is AO, times the height to the base. The height to the base is AP. Why AP is the height to the base? Because of the fact that AP creates 90 degrees with the base AB. So the height is AP over 2. So the area of triangle AOP equals to the base AO. The base AO is R that is equal to 2. The radius of the circle times AP. We already found out that the length of side AP is 5.5. So it is 2 times 5.5 divided by 2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And we left only with 5.5. So in conclusion, we found out that the area of the right triangle AOP is equals to 5.5 square units. So the area of the green shape equals to 2 times the area of triangle AOP, that is 5.5. 2 times 5.5 is 11. In conclusion, we found out actually that the sum of the areas of those two right triangles, the right triangle AOP plus the area of triangle BOP, it is equals to 11 square units. Now we have to subtract from the area of those two right triangles, the sum of the areas of those two right triangles, triangle AOP plus the area of triangle BOP. We have to subtract from this, that is actually the area of quadrilateral APBO, the area of this sector, sector AOB. Okay. So what is the area of sector AOB? What is the area of this sector, sector AOB? The area of this sector, sector AOB, equals to the area of the circle that contains the sector, that is actually pi r square. Pi r square is the area of the circle that contains the sector, times the angle between the legs of the sector. Then this angle between the legs of this sector, sector AOB, is equals to 140 degrees. As you can see in the drawing, 140 degrees over 360 degrees. The radius of this circle r equals to 2, therefore r squared is 2 squared, that is 4. So in total, the area of the circle is 4 pi. So 4 pi times 140 degrees over 360 degrees is equals to the area of the sector AOB. So this expression, 4 pi times 140 degrees over 360 degrees, it is equals to 4.88 square units. So in conclusion, we found out that the area of sector AOB is equals to 4.88 square units. So the area of the green shape is equals to the sum of the areas of those two right triangles. That's actually the area of quadrilateral AOBP. This quadrilateral AOBP. And we already found out that the sum of the areas of those two right triangles, that is actually also the area of quadrilateral AOBP, is equals to 11 square units. And we have to subtract from the area of this quadrilateral AOBP, the area of this sector, sector AOB. And we just right now found out that the area of sector AOB equals to 4.88 square units. So 11 minus 4.88, 888 is equals to 6.111 square units. So in conclusion, found out that the area of the green shape is equals to 6.111 square units. Repeat again. The area of this ring shape is equal to 6.111 square units. So in the next step, I'll summarize the lecture. In this lecture, we found out the area of this green shape. So in the drawing, we have a circle. The radius of this circle r equals to 2. In addition, we have inside this circle the peripheral angle AOB. This is peripheral angle AOB that equals to 70 degrees in its size. And you also have in the drawing, this is the common external point P. From the common external point P, we have two tangents to this circle. Tangent PA, that is tangent to this circle here at point A, and tangent PB, that is tangent to this circle here at point B. Again, our mission is to find out the area of this ring shape. So in the first step, we join points O and B together by a straight line. Point O is the center of the circle. Okay, we join points O and B together by a straight line. What is the definition of line segment OB? Point O is the center of the circle, point B is the point of the circle itself. So this is exactly the definition of a radius. So OB is the radius of this circle, that is equal to 2 units according to what is given us in the question. So the radius OB equals to R, that is equals to 2 units. And we have here the radius OB that is drawn to point B, that is the point of tendency of tangent BP with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BP will be perpendicular to the radius BO. If BP is perpendicular to BO, it means that this angle equals to 90 degrees. Likewise, according to the same rule 1, we have here the radius AOA that is drawn to point A, that is the point of tendency, or tangent AP with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. In the next step, I presented to you the new rule, and we implemented the new rule in our drawing. The new rule is rule 13. According to rule 13, a central angle is twice as large as the peripheral angle that is subtended on the same arc. Repeat again on rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB. This is peripheral angle ACB. This is equals to theta degrees in its size. And this peripheral angle ACB is subtended on this arc RKB. In addition, we have in this drawing the central angle AOB. This central angle AOB is subtended on the same arc RKB. And therefore, according to this rule number 13 or rule 13, whenever you have a central angle that is subtended on the same arc as the peripheral angle, then the central angle will be twice as large as the peripheral angle. And because of the fact that the peripheral angle ACB is equal to theta, therefore the central angle AOB that is subtended on the same arc RKB will be equal to 2 theta. Okay? We can actually implement all 13 in our drawing. Why? Because in our drawing we have the peripheral angle ACB. This is peripheral angle ACB. That is equal to 70 degrees in its size, and it's subtended on this arc RKB. We also have in our drawing, this original drawing, the center angle AOB is also subtended. This center angle AOB is also subtended on the same arc RKB, and therefore, according to rule 13, the center angle AOB will be twice as large as the peripheral angle ACB that is subtended on the same arc RKB. And because of the fact that the peripheral angle ACB equals to 70 degrees, it means that the center angle will be equal to 70 degrees times 2, that is 140 degrees. So actually found out in conclusion that according to rule 13, the center angle AOB will be equal to 140 degrees in its size. In the next step, we join points O and P together by straight line. By joining points O and P, we created two right angles, the right angle AOP and the upper right angle AOP and the lower right angle triangle BOP. In the next step, we actually proved that those two right angles can go into each other. Why those two right angles can go into each other? First of all, side AO of the right angle AOP is equal to side OB of the right angle BOP. They are both there at the eye of this circle, therefore they are equal to each other. Each side equals to 2. That is the radius of this circle. In addition, we have here the common side OP that is belongs to both triangles. So we can write down that OP equals to itself is a common side that belongs to both triangles. And finally, side AP of this right triangle OP is equal to side BP of this right triangle BOP. Those two sides are equal to each other according to rule 2. I will remind you quickly what is rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle and we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, the length of tangent PA is equal to the length of tangent PB. That is to say, PA equals to PB. We can actually implement rule 2 in our drawing. We actually implemented rule 2. We implemented rule 2 because here PA equals to PB. Here in the drawing we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. Okay, again. PA or AP is the same, equals to PB, according to rule 2. So actually proved that all the three sides of the right triangle AOP are correspondingly equal to all the three sides of the lower right triangle BOP. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles are also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding angles, those two corresponding angles must be also equal to each other. So if this angle is alpha, then this angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 140 degrees. Here alpha plus alpha equals to this angle, that is 140 degrees. So we found out that alpha plus alpha equals to 140 degrees. Alpha plus alpha is 2 alpha, that is equal to 140 degrees. We divided this equation by 2 and finally found out that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. So this is angle alpha that is equal to 70 degrees in its size, and this is also angle alpha that is equal to 70 degrees in its size. In the next step, we found out the length of side AP in the right triangle AOP. So in the right triangle AOP, if we focus on the right triangle AOP, it is very easy to see the tangent 70 degrees equals to AP over AO. Again, in the right triangle AOP, tangent 70 degrees equals to AP over AO. And repeat again, in the right triangle AOP, tangent 70 degrees equals to AP over AO. AP is the missing side over AO. AO equals to 2, it is the radius of the circle, so substitute AO by 2. In conclusion, found out that tangent 70 degrees equals to AP over 2. Tangent 70 degrees is 2.75, that's equal to AP over 2. So 2.75 equals to AP over 2. We multiply this expression by 2 and finally found out that the missing side AP equals to 2.75 times 2. 2.75 times 2 is 5.5. In conclusion, found out that the length of this side AP is 5.5 units. Okay. In the next step, I presented to you the notion of sector. What is a sector? A sector is a part of a circle. Here this circle, and the green shape AOB is a sector. It is part of a circle. The green sector AOB consists of two legs. The first leg is AO, the second leg is BO. Both those two legs are the radii of the circle. Of the circle is equal to R, therefore they are equal to each other. And the green sector AOB consists also the RKB. The RKB is located between the two legs, and the angle between those two legs AO and BO is angle theta. You can look at a sector as a slice of a pizza or a slice of a cake. Okay? So the area of this sector AOB equals to the area of this circle that contains the sector, that is pi r squared, times the angle between the legs of this sector, that is theta, over 360 degrees. I repeat again, the area of this sector AOB, the green sector AOB, equals to pi r squared times theta over 360 degrees. Repeat again that our mission is to find out the area of this green shape. What is the area of this green shape? The area of this green shape equals to the area of the right triangle, the upper right triangle AOP, plus the area of the lower right triangle BOP. So the sum of the areas of those two right triangles will give us the area of this quadrilateral AOBP. Okay, the sum of the areas of those two right triangles will give us exactly the area of this quadrilateral AOBP. So we have to subtract from the area of this quadrilateral AOBP the area of this sector AOB. And the result will be exactly the area of this green shape. I repeat again, the area of the green shape in total equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. This will give us the area of quadrilateral AOBP, and we have to subtract from the area of quadrilateral AOP the area of the sector AOB. And because of the fact that those two right triangles can go into each other, we will conclude that they also have the same areas. Okay, those two right triangles have the same areas. Therefore, we can add the area, we can substitute the area of the right lower triangle BOP by the area of this right triangle AOP, because they have the same areas. So here, the area of the green shape equals to the area of triangle AOP plus the area of triangle BOP, but because of the fact that the area of triangle AOP is equals to the area of triangle BOP, we can substitute the area of triangle BOP by the area of triangle AOP. So we did it here, we substitute the area of triangle BOP by the area of triangle AOP. And therefore we got that the area of triangle AOP equals to the area of triangle AOP plus the area of triangle AOP minus the area of sector AOP. So the area of triangle AOP plus the area of triangle AOP is 2 times the area of triangle AOP minus the area of sector AOB. Then we calculated the area of triangle AOP. The area of any triangle equals to the base of the triangle times the height of the base over 2. So the area of this triangle AOP equals to the base is AO and the height is AP. Again, the base is AO, the height is AP divided by 2. AO is 2, AP is 5.5 divided by 2. Here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled and we left only with 5.5. In conclusion, found out that the area of this right upper triangle AOP is equals to 5.5 square units. And because of the fact that the area of this right triangle AOP is equals to the area of this lower triangle BOP, so we can multiply the area of this right triangle by 2, and in this way we will get the area of those two right triangles together. The sum of the areas of those two right triangles. That's actually the area of quadrilateral AOBP. Okay, and therefore 2 times the area of triangle AOP, that is 5.5, will give us the area of quadrilateral AOBP, that is 11 square units. 2.5 is 11 square units. Okay, so in conclusion, found out that 2 times the area of triangle AOP, that is actually the area of triangle AOBP, and the area of quadrilateral AOBP is equals to 11 square units, and we have to subtract from the area of triangle of quadrilateral AOBP that is equals to 11 square units, the area of sector AOB. Okay, so what is the area of sector AOB? What is the area of the sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r square. The area of this circle that contains sector AOB is pi r square, because the radius is r. So the area of pi r square, so it is pi r square times the angle between the legs of this sector. The angle between the legs of this sector is 140 degrees over 360 degrees. So r is 2, therefore r square is 2 squared, that is 4. So in total, the area of the circle is pi r squared, that is 4 pi times 140 degrees over 360 degrees. The value of this expression in total, 4 pi times 140 degrees over 360 degrees, it is 4.888 square units. 4.888 square units. In conclusion, found out that the area of sector AOB equals to 4.888 square units. So the area of the green shape equals to the area of quadrilateral AOBP. We already found out that the area of quadrilateral AOBP is equals to 11 square units. And we have to subtract from the area of this quadrilateral AOBP the area of this sector AOB. And we just right now found out that the area of sector AOB is equals to 4.888 square units. So 11 minus 4.888 equals to the area of the green shape. 11 minus 4.888 is 6.111 square units. So in conclusion, found out that the area of the green shape equals to 6.111 square units. Repeat again, found out that the area of this green shape equals to 6.111 square units. Okay, thank you very much.